Hello, do you have signals in your mobile? You might be happy to be in good mobile signal or good Wi-Fi signals as you can do more fun. Have you ever thought of what is the meaning of these signals? What are those signals or what is the ordinary sunlight is made up of actually? Well, I'm sure most of you haven't. If it is so, do you want to know it? Its meaning, mathematics, concepts and applications? If the answer is yes, then this lecture is going to be interesting for you. Even if your answer is no, then also you need to think of it. Otherwise, you are going to be bored. So, welcome to the lectures on electromagnetic waves. Let us start with dividing this topic of electromagnetic waves into three broad parts. These parts are mathematical tools, fundamental laws and Maxwell equations, and the solutions of Maxwell equations. This will be the outline of our first part, and after completing this part, you must be able to answer about the meaning of field, its type, rates of variations, and to solve some easy problems on differential and integral calculus of vectors. Of course, the prerequisites are the knowledge of vectors and scalars and differential and integral calculus of the functions. The field. In philosophy of physics, a field is the region of influence by a source of the effect causing agency. And to deal with it mathematically, it is a function of space coordinates. So, a field is represented by a multi-dimensional mathematical function which may be scalar to give scalar field or it may be a vector to give vector field. The examples of scalar field may be the distribution of temperature in the room. How? The temperature varies in the room with space coordinates. It may have different values at the doors and at the corners of the room. A potential around a charge distribution is also a scalar field because potential is scalar quantity varying with space coordinates. Other examples may be height of a hill and many more. The well-known example of vector field is electric field or magnetic field around charge or current distribution respectively. Another example of vector field may be the Earth's magnetic field which keeps us away from solar radiation storms and gravitational field of moon on the Earth responsible for tides on the Earth. Let us start with temperature distribution in space. The temperature T as a function of x, y and z forms a scalar field. Clearly, the value of temperature at each coordinate of space is different. Now the question is how to know the temperature at any point if it is known at a given reference point. You can do it easily if you have the information of rate of variation of the field or temperature with space coordinates. Suppose T1 as a function of x, y and z is the temperature at any point P1 and you want to know the temperature T2 which depends on the coordinates of the point P2. Let dl is the differential distance vector or the displacement vector of point P2 with respect to P1. dl is given by this expression in terms of components dx, dy and dz along all three mutually perpendicular directions. The components dx, dy and dz are the differential distances required to be travelled along x, y or z axis in order to reach point P2 from P1. These components can be found by dot product of unit vectors along x, y or z directions with dl. Now the total change dt in temperature in moving from point P1 to P2 is given by this in differential calculus. In this, del T over del X is the change in temperature T by moving unit distance along x-axis, and the second and third terms can be explained similarly. Now, if you put the values of dx, dy and dz, you get this. Now you can easily write it as this. Here, the second term, dl, is the displacement vector. So the first term must be the rate of change of scalar field temperature with respect to the position. This term, which looks like a vector quantity because it contains I cap, j cap and k cap, is known as gradient of scalar field T and is written as this. This symbol is pronounced as del operator. As another example, you may think of a hill. The height h of hill is a function of two coordinates x and y. Then what is the meaning of gradient of h? Let us check. The gradient of height h is given by this function. By the help of gradient of h, you can find the change in its height as you move on hill in any direction dl. So this is equivalent to the slope of the hill at any point in question. Sometimes it is called similar to the vector differentiation. Since it is a vector, then the question is, what is its direction? The total change in h is given by this, where theta is the angle between gradient of h and our movement dl. Now, to find the maximum change in h, you can check many directions of displacement. The one in which the dh is maximum must be in the direction of gradient of h, because in that case theta will be 0. So the direction of dl or our movement and the direction of gradient of h are the same. So the direction of maximum variation or slope of the field is direction of gradient of scalar field. Imagine it is raining on the hill. You can notice that the water flows in the path of maximum slope of the hill or in the direction of gradient of h at each point of its path. This del operator is very interesting as it does have unit vectors along x, y and z axis, but it has no magnitude. Can you see? So it cannot be a vector at all as there is no magnitude, but it is an instruction to be applied on a scalar function or field to provide gradient of that field. Thus it is called a vector operator. It behaves like vector in terms of scalar and vector products with other vectors. Let us see what happens if we operate it with other vector functions or vector fields via dot product or cross product. When del operator is operated on any vector field A via dot product, it gives the divergence of a vector. The property of divergence is like its name. The divergence of any vector shows that how much field is diverging from any point of question or how much field is converging to that point. If the divergence of vector field is positive, it shows that the vector is diverging at that point. And if the divergence of A is negative, then that point becomes sinc for that vector. If you operate del operator on any vector field A via cross product, then it is known as the curl of the vector. Curl of a vector can be computed with simple method of cross product of any two vectors. Like the divergence of any vector field was a scalar quantity because there is no I cap, j cap or k cap in that expression. So the divergence of a vector field is a scalar function. But the curl of a vector field is a vector itself. The property of the curl are as its name. Curl of any vector shows how much rotation in that vector is at any point of question. So if the curl is a positive vector, then the rotations are anticlockwise. While if the curl is a negative quantity, then the rotations are clockwise in that vector at any point of question. If you have a current carrying wire, then the magnetic field around that wire is rotating with the center at that wire. So there is a curl in magnetic field around any current carrying wire. Up to now, you have come to know about del operator, and this is operated on a scalar field and on vector field. A vector can be written in terms of its components along x, y and z axis. When del operator is operated on scalar field T and vector field A, then it can give gradient of a scalar which is a vector, the divergence of a vector field which is a scalar, and curl of the vector field which is again a vector. Here the gradient of a scalar is equivalent to slope of the field. Divergence of a vector gives the amount of vector which is expanding or contracting at any point. The curl of any vector field gives the amount of rotation of that vector around any point of a question. If we wish to compute higher order derivatives, then for gradient we can have two types of second order derivatives, which are the divergence of gradient, because gradient is a vector, and this vector can be operated by del operator via cross product to give curl of the gradient, which is 0. You can check it by taking any random scalar field. The divergence of a gradient is another quantity known as Laplacian of the scalar field. Laplacian of the scalar field is given by this expression, in which what you will have to do is to take double derivative of the scalar field with respect to x, y and z, and then add all these things. The divergence of a vector field is a scalar. We can take the gradient of this divergence, and in physics this is of not very much importance. For a curl, which is a vector, we can have either divergence or curl. The divergence of the curl is 0. You can check this also by taking any random vector field. The curl of the curl is given by this identity. You need to learn it because we are going to use it in our lecture of electromagnetic waves. Here this second term is the Laplacian of a vector. The definition of Laplacian of a vector is different than the definition of Laplacian of a scalar field. This is given by this expression. In this, what you will have to do is you will calculate the Laplacian of each of the component of that vector field and then replace those components with their Laplacians. This all was the differential calculus of the fields. After differential calculus, let us come to integral calculus of vector and scalar fields. Like ordinary integral of a function with fields also, there are three types of integrals, namely line integral, surface integral and volume integral. These may be regarded as single, double and triple integrals. In words, these may seem to be very simple, yet they appear in all the fundamental laws of electromagnetism. Here, the line integral is over a definite path, and to show it, we put C for curve or P for path at this place. Surface integral is over a given surface, so S is put here, and the volume integral is over a volume tau or simply V, so we put tau or V at this place. If the path in the line integral and the surface in the surface integral are closed, then these line integral and surface integral are represented by this symbol, and these are known as closed line integral or closed surface integral. The line integral of the force on a particle over a given path is the work done by the force on the particle, and the surface integral of a field over a surface is the flux of the field linked to the surface. And at last, the volume integral of a volumetric charge density is the total charge in a given volume, or the volume integral of mass density over the given volume is the total mass of the object. These integrals are frequently used in laws of electromagnetism. Sometimes what happens is that the different type of integrals appear in a single equation. When it happens, we need to convert all types of integral terms into the same type of integral for any conclusion. This mathematics is done in two mathematical theorems. These theorems can be viewed for an easy understanding as the integral of a differential of a function lent to the given function. The integral of a derivative of a function over an interval is equal to the value of that function at the boundary or the extremities of the integral, like this. Here, the boundary of a volume is the closed surface, and the boundary of a surface is a closed line. These two theorems are Gauss's divergence theorem and Stokes theorem. Gauss theorem says that the divergence of a vector field A over a volume V is equal to closed surface integral of that vector over a surface which encloses this volume. The right hand side is the total flux attached with this closed surface. So, in words, the Gauss theorem states that the total outward flux of a vector field A at a closed surface S is same as the volume integral of the divergence of the field. Next, the Stokes theorem is given by this equation, and it says that the surface integral of curl of a vector field is equal to the closed line integral of that vector field over the path which encloses the surface. In words, it is the circulation of a vector field around a closed path L is equal to the surface integral of the curl of the given vector field over a surface S bounded by this path L. At this point, you must be able to tell about the divergence, gradient and curl of a vector field and scalar field. You must tell about the Laplacian of a scalar field as well as of vector field. Next, you must be informed about the three types of integrals of the field and these two theorems to interconnect the surface integral, line integral and volume integral. In the next video, you will learn about four fundamental equations or the laws of electrodynamics.